Hello everyone and welcome. In this presentation, I am going to explore how agile project management principles commonly used in software industries can significantly benefit design for manufacturability in mechanical engineering. As engineers, we are not just responsible for designing parts, we are also future project leads. And while DFM handbooks guide our technical decisions, it's how we manage the design process that determines success in real world production. So today, let's explore how merging agile thinking with DFM practices can lead to faster iterations, better manufacturability, and more collaborative engineering. Here's a quick look at the roadmap that I will be sharing. We'll begin by discussing the growing role of design engineers as project managers and why project management is essential when aiming for manufacturable designs. Next, we'll explore project management fundamentals, covering the typical life cycle phases and how these align with the engineering design process. We'll then examine execution methodologies, comparing traditional linear approaches like waterfall with iterative models such as Agile and how they will impact design workflows. After that, we'll dive into the Agile philosophy, its core values, and the Scrum framework, including key roles and processes. Building on that, we'll look at how Scrum can be applied directly within engineering and DFM, especially for rapid prototyping, feedback loops, and supplier collaboration. Then I'll share case studies and research-backed insights from IDEO, Harvard, and industry examples to show how Agile and DFM work together in real-world settings. So the question is like why project management matters in DFM. One of the biggest challenges in DFM isn't the lack of technical tools. It's the timing and management of how those rules are used. So it's not about the geometry only, it's about managing trade-offs. So, in real world projects, manufacturability issues often appear too late when the CAD is done, vendors are selected, and tooling is already in progress. This leads to costly rework delays and frustrations. So, this is why project management skills are really, especially agile methods, are becoming essential for design engineer. So, design engineers' roles are critical for the decision making process. And DFM doesn't fail because designers lack technical tools. It fails because we don't manage design workflows adaptively. So now let's understand the fundamentals of project management and project management from the perspective of design engineers. So project management is the disciplined application of skills, tools, and methods to meet requirements within defined time, cost, and scope constraints. It's not just about scheduling, it's about making smart, strategic decisions throughout the life of a design project. For a design engineer, the job doesn't stop at CAD or simulation. You are constantly working across teams with manufacturing, quality, supply chain, and even suppliers. That means you are managing dependencies, decisions, and risks, whether you realize it or not. That's why we say design engineers are de facto project managers. On the right, you will see how project management directly supports DFM. It sets clear timelines for the iterations and design reviews. It tracks dependencies between CAD simulation, prototyping, and tooling. It facilitates early manufacturability and cost feasibility checks. It gives structure to risk management like tolerance stack-ups or material changes. And it ensures concurrent engineering, synchronized, not chaotic. The triangle at the bottom reminds us of a classic project constraint model. Time, cost, and quality are always in balance with scope. Project management helps you hold that balance, especially in high stakes product development. So, the better you are at managing your project, the better your design will perform, not just in simulation, but in production. In product development, especially when design for manufacturability is a key goal, it's not just enough to just design well. You also need to manage the process strategically. What you are seeing here is the typical project lifecycle curve, showing how effort changes over time across four major phases: defining, planning, executing, and closing. In the defining phase, the project begins by establishing goals, technical specifications, tasks, and responsibilities. For a design engineer, this is when you align with stakeholders, clarify scope, and identify any early manufacturability constraint. In planning, effort ramps up as you develop detailed schedules, budgets, and resource allocations. This is where key DFM decisions should be made, like selecting materials, manufacturing processes, and planning design checkpoints for feasibility reviews. Execution is where most of the technical work happens: CAD modeling, simulation, DFM checks, etc. And in finally, in closing phase, you wrap up the project by validating outcomes, transferring documents to manufacturing, releasing resources, and documenting lessons learned. As you can see, the cost of design errors increasing exponentially the later they're discovered, which is why DFM needs to be embedded early in the cycle. Understanding this structured flow allows design engineers to act not just as the creators but also as the leaders who can anticipate, align, and deliver manufacturability solution efficiently. In this slide, I have aligned the engineering design process with the project management lifecycle to show how each design phase naturally maps to a structured project management stage. On the left, we start with traditional steps in the design process, defining the problem, researching, specifying requirements, and developing solutions. These align closely with the initiation and planning phases in project management, where we identify manufacturability goals, stakeholder needs, and document DFM constraints. As we move towards execution, tasks like brainstorming, prototyping, and running DFM tools such as DFM Express or Granta fit perfectly under project execution. Here, project management helps us to stay on schedule and ensure our design decisions align with the manufacturability capability. In later stages, monitoring and controlling ensure our test results or supplier feedback are used to refine the design efficiently instead of pushing changes too late. Finally, we wrap up with the project closing, which matches the communication of results, documentation, handoff, and lessons learned. Overall, the message is clear. Good design and good project management are not separate, they are integrated, especially when manufacturability matters. To support this concept, I have also included a short YouTube video link on the slide that shows this alignment visually from the problem definition through iterative prototyping and delivery. Now I'll quickly go through all the project life cycle phases. First one is the defining phase or the initiation phase. It is where we set the foundations of entire project. And in DFM, this is where many critical missteps can be avoided. So in defining phase, we define the goals and the problem statements, identify key stakeholders, outline high-level deliverables, and conduct technical and manufacturability feasibility assessments. So we don't want to treat manufacturability as an afterthought here. So traditional designs often begin in isolation and hit roadblocks later. But when we manage the design like a project, initiation brings clarity, alignment, and visibility upfront, not as a reaction to failure. This phase is also where we use SMART objectives to formalize our goals. So SMART stands for specific, measurable, assignable, realistic, and time related. So, for example, instead of vaguely saying design a new product, we say we developed a retractable wheel luggage model for market within 6 months and around 200,000 US dollars budget. So that transfer an idea into an actionable project with scope, resources, and timeline clearly defined, making it far from likely to succeed in both design and manufacturability. Also, in initiation phase, once we outline the project's purpose and stakeholders, the next priority is defining its scope and doing it carefully. This slide highlights three tools that are critical in the early stage. First, we must estimate time, cost, and resources needs. Two approaches are commonly used top-down estimates, which are faster and ideal for conceptual planning and rough sizing, and the bottom-up estimates, which are more detailed and used for budgeting, scheduling, and resource decisions. Both are essential. Top-down helps get early buy-in, while bottom-up supports accuracy and control. However, if we fail to control scope, we risk what's known as scope creep, the tendency for project goals and specifications to expand over time. This often leads to delays, cost overruns, and rework. Examples like the Denver's airport baggage system or the Big Dig in Boston show how critical this is, even outside software or civil projects. That's where the work breakdown structure or WBS become invaluable. By breaking down the scope into smaller, clearly defined work packages, we can create an outline that guides the project execution, team responsibilities, and future review points. A well-structured WBS doesn't just organize the project, it's the foundation for DFM focused planning, ensuring that cost, complexity, and manufacturability are considered from the start. Once the scope is defined and broken down into a work breakdown structure, the next step is planning, where strategy meets structure. The diagram here illustrates the core components of the project planning process. We begin with the WBS, which breaks the project into manageable chunks. These feed into a network of activities, essentially a map of what tasks depend on what others. From this network, we generate detailed resources and cost schedules. All of this must be evaluated through the lens of risk. For example, what happens if the selected material has long lead times or if tolerances in DFM critical joint aren't met? The final outcome of this phase is a master plan, a cohesive roadmap that aligns deliverable timelines, risks, and resource usage. For DFM, planning is where many cost-saving and visibility-enhancing decisions are locked in, whether it's a vendor selection, process constraints, or tooling timelines. This is where the manufacturability of a design is proactively managed. The next third phase is a execution phase. It is where design engineers spend the most time. It's where ideas turn into manufacturable components. This is where we develop CAD models, perform DFM express checks, validate material selections from Renta, and work closely with manufacturing engineers to ensure designs are not only functional but also feasible to build. For example, if we are designing an injection molded part, this is when we apply specific rules, uniform wall thickness, draft angles, and rib spacings. If it's die-cast, we review ejector pins locations, cooling channels, and surface finish. This phase also includes building and testing prototypes, collecting supplier feedback, and iterating based on what we learn. A design may look perfect on paper, but if it can't be assembled, machined, or inspected efficiently, it's not manufacturable. In DFM, execution is where trade-offs become reality. Design engineers must stay agile, respond to issues quickly, and ensure that every revision moves the product closer to scalable quality solution. The last phase of project lifecycle is the closing phase, which is often overlooked, but it's critical, especially for continuous improvement in DFM. This is where we finalize project activities, hand off deliverables, and reflect on what went well and what didn't well. The diagram here shows three closure pillars. First, we wrap up by confirming all deliverables are complete and clients, vendors, and facilities are off-boarded. Second, we conduct a project audit, a structured review where we analyze design decisions, tooling changes, manufacturability changes, challenges, and iterations delays. These are captured as lessons learned. Finally, we conduct team and individual evaluations, a chance to assess collaboration, and identify communication bottlenecks, and reinforce the integration of project management with design execution. For design engineers, this is where we transition from project done to knowledge gained. The success of your next project may depend on what you documented here. Now that we have covered the life cycle phases, let's zoom out and look at the bigger picture, the methodologies we use to manage projects. A project management methodology is essential a structured approach, a set of principles and practices that guide how a project moves from start to finish. These methodologies can generally be classified as either linear or iterative. In linear models, like the waterfall approach, each phase must be completed before the next begins. Think of it like a building a bridge. Once the concrete sets, there's no going back to move the pillars. Waterfall emerged in the 1970s and works best when goals are stable and budget are tight. But it's rigid. Late stage changes like manufacturing redesigns are difficult to implement. In contrast, Agile, which gained popularity in the early 2000s, is iterative and adaptive methodology. It breaks work into short cycles called sprints, enabling continuous feedback and evolution. Agile is led by a Scrum Master who facilitates rather than directs. This makes it ideal for design and DFM projects where requirements evolve, manufacturability constraints appear midstream, and quick prototyping is valuable. So, in short, waterfall gives you control, agile gives you flexibility. And for DFM, where design needs to be aligned with manufacturing realities, fast, agile often holds the edge. Let's take a quick history lesson so you can better understand how and why Agile became such a powerful and popular approach to project management. Agile methodologies didn't just appear overnight, they emerged organically during the 1990s. As the software industry was booming, startups like Google were racing to build innovative products under tight timelines, while established tech giants like IBM and Microsoft were experimenting with faster, more adaptive workflows to remain competitive in a rapidly changing market. Teams realized that traditional linear models like waterfall simply couldn't keep up with the need for speed, flexibility, and user feedback. That led to a growing shift towards iterative methods, with Scrum and extreme programming taking shape as early frameworks. In 2001, this movement was formally captured in the Agile Manifesto. a simple but powerful document that emphasized individuals and interactions, working solutions, customer collaboration, and responding to change over rigid plans. As shown in the timeline here, Agile Foundation goes back even further to ideas rooted in the Toyota Production System, Kanban, and early studies of team behavior and system thinking. Over the decades, Agile evolved through phases of emergence, democratization, and now modernization, with frameworks like Spotify model, SAFE, and modern Agile being applied for beyond software into hardware, manufacturing, education, and of course, design engineering. Today, Agile isn't just a methodology, it's a mindset for working smarter, adapting faster, and delivering value continuously. And when applied to design for manufacturability, it allows engineers to iterate with purpose, engage stakeholders early, and avoid costly late-stage surprises. Now that we have seen how Agile evolved, let's explore the 12 principles that guide Agile teams in their day-to-day decisions. First one, satisfy customers through early and continuous delivery, welcome changing requirements even late in development, then deliver working product frequently, then close collaboration between business and developers, build around motivated individuals, trust them, face-to-face conversation is most effective, then working product is the primary measure of progress, sustainable development with constant pace, continuous attention to technical excellence, simplicity, the art of maximizing the amount of work not done is essential. Then self-organizing teams produce best architectures, requirements, and designs. Regular reflection and adjustment. And so these are the 12 principles of the Agile Manifesto. So the principle encourages regular reflection and adjustment, something many DFM projects could benefit from earlier, rather than saving feedback for them. These principles are what make Agile more than just a set of tools. They make it a flexible, human-centered approach to solving complex problems. So how does Agile actually fit into the world of engineering design and manufacturability? First, Agile's iterative prototyping process allows us to test early CAD models or 3D prints, helping verify DFM constraints like the wall thickness, draft angles, and tolerances before we commit to tooling. Second, it enables early manufacturability checks. Each Agile iterations become an opportunity to run tools. And the third one is Agile promotes ongoing collaboration with customers and suppliers. Stakeholders aren't just consulted at the end, they are involved continuously through demos and sprint reviews. Fourth is the Agile strengthens cross-disciplinary feedback loops. For example, during the design iterations, manufacturers can flag parts that aren't moldable or call out fasteners that might too complex or too expensive. And finally, Agile supports rapid redesign. This fail fast, learn fast mindset allows teams to adjust geometry, swap materials, or simplify components, all before tooling begins. The visual here shows the philosophy in action, evolving a rough product into a finished one through quick, structured learning loops. This is what makes Agile so powerful for DFM. Design decisions evolve with the real-world feasibility in mind. So, Agile project management methodology is not one set of method, but it is a family of methods designed to respond to the challenges of unpredictable projects. Some of the popular methods are listed here. Scrum, Extreme Programming, Rapid Product Development, Dynamic Systems Development Methods, RUP, Crystal Clear, Learn Development, Agile Modeling, etc. Yeah, so out of all the agile methodologies shown earlier in the slide, the Scrum, which is most widely used agile methodology, I'll talk more about that. The Scrum is a lightweight, iterative, and incremental framework designed to help teams tackle complex problems while continuously delivering high-value outcomes. At its core, Scrum is built on empirism, the idea that knowledge comes from experience and that decisions should be based on what is observed, not just what's assumed. So Scrum operates through a defined structure made up of sprints, which is time box development cycles, usually less than a month, where a usable product increment is delivered. Next is events. This includes sprint planning, daily scrums, and sprint reviews and retrospectives, all designed to inspect progress and adapt. The artifacts, the key outputs in a scrums are the product backlog, sprint backlog, and the increment. Each helps maintain transparency and focus. Scrum is also anchored in five core values: commitment to the team's goals, courage to tackle uncertainty, focus on spirit priorities, openness about progress and setbacks, and respect for every team member's contribution. The framework defines three primary roles: the product owner, who maximizes values and manages the backlog, the developers, who plan, build, and deliver the work. We can also call them the team members, and the Scrum Masters, who ensures Scrum is followed and facilitates continuous improvement. It's kind of a mentor you call to a team, or you call a coach to a team. So overall, Scrum provides just enough structure to stay on track while still giving teams the flexibility to iterate, learn, and deliver rapidly, making it a natural fit for the modern engineering and DFM environments. Now let's talk about how Scrum integrates directly with the design for manufacturability. So one of the biggest advantages of Scrum is that each sprint acts as a dedicated iteration for prototyping. These time box cycles allow us to generate functional CAD models or early prototypes that can be tested for manufacturability. That means issues like any kind of design violations can be eliminated or solved earlier in in the designing phase. So Scrum also provides cross-function collaborations in various engineering domains and engineering teams. So there is also backlog-driven tasking in the Scrum, so which helps for the design in the roadmap. So tasks like tolerance analysis, any DFM checks, or material optimization can be part of this sprint backlog. And there is also retrospective in the Scrum, so which help designers to look for the design teams and its decisions made. So this can be reflect on the late stage manufacturability issues and improve processes for the early vendor engagement or GD&T training, etc. So I'll share a real life example from the IDEO company, which is California-based Palo Alto-based company, and it is a premium design firms in the world. They are responsible for a wide range of product innovations, including the first Apple mouse, Heads Airflow tennis racket, Zilli's salad spinner, and Nokia's N-Gage smartphones. IDEO's main client include Pepsi Cola, 3M, Logitech, Nike, and HBO. IDEO has won more of the Business Week's IDSA Industrial Design Excellence Awards than any other firm. So IDEO's approach to product design relies heavily on an iterative development process, in which product prototypes are used to explore and further refine product ideas. CEO Tim Brown states that the goal of prototyping is to learn about the strengths and weaknesses of the idea and identify new directions that the prototype might take. So, for example, IDEO worked with Procter and Gamble to develop a new Crest toothpaste tube. The challenge was to improve the traditional screw-on cap, which always gets gummed up with toothpaste. IDEO's first solution was a pop-on, pop-off cap. However, when designers created rough prototypes and watched people use them, they quickly noticed that users kept trying to unscrew the cap, even though they were told how it worked. The designer concluded that the accents was a ingrained habit that would probably impossible to break. So they came up with a hybrid, a twist-off cap that had a short thread but would still be easy to clean. Focused prototyping resolves critical problems one by one. Brown recommends that prototypes should only take as much time and effort needed to generate useful feedback and evolve an idea. Another example is the Vector chair example. So IDEO was working on a chair for Vecta Company, a high-end office furniture manufacturer. The project had evolved to the point where the height adjustment lever that tilted with the chair became critical. The team didn't build the whole chair or even the tilt mechanism. They just built the little lever and its interface with the tilt mechanism. It took only a couple of hours. When finished, the prototype quickly demonstrated that the principle would work. Also, let's look at how Scrum has been successfully applied in real-world product design scenarios, especially when manufacturability plays a central role. The first example comes from automotive sector. A team working on a cooling duct for electrical vehicle adopted Scrum to manage the evolving performance targets while keeping manufacturability in check. So in sprint one, they focused on conceptual geometry and ran airflow simulations. In Sprint 2, they moved into DFM Express analysis and created a 3D printed prototype. And in Sprint 3, supplier feedback promoted key redesigns to improve moldability. So instead of discovering manufacturability issues late, they integrated that feedback sprint by sprint. Now, on the medical side, team designing an injection molded housing for a regulated device use Scrum to reduce risk and ensure compliance. Each sprint focused on usability, tolerancing, and FDA compliance. They included manufacturing partners in sprint reviews, turning them from late-stage reviewers into early-stage collaborators. And the result, a final design that went to tooling with zero post-tooling iterations. These examples show how Scrum isn't just for managing tasks, it's a powerful framework for integrating DFM principles, catching issues early, and delivering manufacturable designs faster. As we close, let's reflect on a few key points. First, Agile is just for not just for software anymore. Its iterative feedback-driven approach is proving incredibly powerful in the world of physical product development and manufacturing. Early prototyping and rapid iteration make DFM smarter. Agile principles encourage us to test early and often, catching manufacturability issues before they become expensive mistakes. Integration is everything. Agile frameworks, especially Scrum, facilitate seamless collaboration between designers and production engineers. That's where real DFM value emerges from cross-functional engagement. Think fail fast, learn faster. The goal isn't perfection on the first try, it's a fast, low cost iteration that drives better decision and part optimization. And finally, Agile plus DFM is the best fit model when uncertainty is high. Whether you are in early stage innovation or tackling complex assemblies, Agile gives you a structured, adaptive way to move forward. Build only what's needed as fast as possible with feedback at every step. That's Agile DFM. Yes, so for this presentation, these are the some of the references which I use to make the presentation. So thank you for listening me. If you have any questions or would like to explore specific topics further, please feel free to reach out. I will be happy to discuss or share more insights. Thank you.